Hello everyone, welcome to your fifth tutorial for ECE 457A. In this tutorial we're going to talk about uh, traveling salesman problem and how to use ACO and colony optimization algorithm to solve this problem. So let's get started. So the traveling salesman problem is a widely studied combinatorial optimization problem. So according to Wikipedia, it is a subfield of mathematical optimization that consists of finding an optimal object from a finite set of objects. So the problem says that we are given a set of cities and a cost to travel from one city to another. So usually this cost is the distance between the cities. Now we want to identify the tour that will allow a salesman to visit each city only once, starting and ending in the same city, at the minimum cost, obviously. So the problem is said to be NP-complete, non-deterministic polynomial time complete, which means that there is no known polynomial time algorithm to solve this problem. For more information on polynomial time, you can visit MathWorld Wolfram. There's good information about that in there. As an example, this image shows the solution to the problem of finding the shortest route between 48 states of the United States. So this can be an example of traveling salesman. We are visiting each state only once, and this is said to be like these routes are the shortest or at the minimum cost routes that one can find. So it's hard to find such clean or neat solutions for such problems. So not all solutions can be like this, but this is the optimal one for this problem. Here in the last page, you can find some resources that I use for these slides, and you can also refer to for more information. Okay, let's move on to the code part and go through the algorithm. So I actually created a new config file, config ACO, and we have a cost function here. The ACO algorithm is implemented here for you in the search algorithms, and we have a new main. So this new cost function actually calculates the distance between vertices. So we have a couple of nodes. These nodes can actually represent the uh, situation of the, for example, cities or the city coordinates. Okay, so this function actually calculates the Euclidean distance between two nodes or between two cities. For example, we have uh, city A located here and city B located here, so the distance between them will be 5. So this function takes a list of lists and outputs a graph that consists of the like a 2 by 2 matrix that consists of the distances of the cities 2 by 2. Here we have our config file, number of ants, vertices. So actually vertices show the location of the cities on the like on the map or in a coordinate system. Um, you can tweak the numbers, use different pairs just to come up with new problems. Then we have maximum number of iterations, maximum number of iterations for ants, alpha, and beta, which are some hyperparameters in your algorithm, in a CO algorithm. The pheromone decay, starting vertex, and one-time visit false or true, stopping vertex, and visit all vertices. TSP is traveling salesman problem. Okay, now let's move on to the algorithm. So we introduce a set of vertices and input it to the cost function and take the graph, which is a 2 by 2 matrix that represents the uh, distance values between nodes or vertices in the graph. Calculate the number of vertices, and after that, we need to initialize the pheromone for each edge, like to a small positive random value at the starting of the algorithm. Then we need to save our or store our best solution and TQDM. Here is the main loop. So according to the algorithm here, while not converged, for this part we're using the maximum number of iterations. We are doing that for each ant k here. So if you have a starting vertex, we're going to use that, and we will place all ends at that source vertex. But if you don't have any starting vertex, like here, starting vertex here, for example, it's 5 in this example. If you don't have one, we're giving it a random value. And for that specific end, that will be the current vertex. So this value will be different for the next end. We're placing each end in a vertex selected randomly. And we are going to save whether we have visited a vertex or not, and the solution for that, and the cost for that here. All right. Now in this part, we need to store the probabilities, because for further on, we need to use them in here. In here, as you know, the formula for that. Yes, this one. We're using this one in this algorithm. So we're using the inverse of the cost, which is the obviously the distance. We said alpha and beta that are hyperparameters. Any values between 0 and 1, scalar hyperparameters. So we're storing the distances, and this is the inverse of the distance to the power of beta, and this is the pheromone value to the power of alpha, and we're appending that to the probabilities, Then we use those probabilities to like each probability here and add them together to create the denominator for the for that part of the probabilities to somehow normalize the probabilities so they add up to 1. And these are our probabilities over here. Then we need to choose our next vertex, which is chosen actually randomly. And we make sure that we have visited that vertex. So this visited part is important because in the traveling salesman problem, we need to know which nodes we have visited and which nodes we have not. That's an important part. And then we need for the termination of a single ant, we need some conditions. Also, these conditions are needed for different problem. For example, if you are solving the traveling salesman problem, you need to make sure that each node is actually visited only once, and the starting and the end node are actually, or stopping node are the same. But there are some problems. The starting and end stopping nodes, they do not need to be the same thing because maybe we want to travel from one place to the other place and that place is our destination and we need to find the shortest path to that destination. So it doesn't matter maybe if you visit some of the nodes twice or more than 2 times. So actually these conditions here are placed here and you can tweak them using these values over here. These are for your problems, whether you are solving the traveling salesman problem or you're solving another problem that has no such conditions. And after that, you need to update the best cost and the best solution, append it to store it. Then we need to decrement or evaporate the pheromones gradually. Here, this part. Yes, this is the pheromone decay. And then update or strengthen the pheromones gradually, which actually is this part for each edge. Then we're updating the progress bar in close. Okay, let's run the algorithm for different problems. So here, for example, we want to solve the traveling salesman problem. So for traveling salesman problem, null for traveling salesman problem. This maximum number of iterations for ants must be null. Here, null or int for traveling salesman, so it doesn't matter the starting vertex. Well, the starting vertex here actually must be also the stopping vertex in the traveling salesman problem. So null for traveling salesman, let's say 5, it can be null or int, so it doesn't matter. And so one time visit. So we need to have this condition that each vertex is actually visited only once in the traveling salesman problem. So this must be true. And the stopping vertex is null and visit all vertices false. So this must be true for traveling salesman because in traveling salesman we want to visit all nodes or all cities. And also the important part, traveling salesman. Is this a traveling salesman problem? Yes, so true. Um okay, let's run the code. think we don't need this one here. So we're getting the calculate distance as a cost function. We're passing that to this function ACO in the search algorithms and getting all the variables and hyperparameters from the config ACO. All right. So here, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 nodes, or aka 8 cities that we want to visit only once, and the starting and stopping points must be the same. Um, so we started at node number 5. 1, 2, 3, 4, 5, which is like 4 in Python. So this one is 5. So 0, 1, 2, 3, 4, 5. Then we move on to 4, after that to 6, 7, 2, 3, 0, 1, and 5. So starting and stopping points uh, are the same, and we have visited each city only once. And the best cost is 16, which is the total distance traveled. Now maybe we want to have different problem. For example, this one needs to be null for TSP. Let's say, I don't know, maybe 0 is a stopping vertex. Let's leave starting vertex at 5. One time is it true or false? It doesn't matter. Let's leave it at true. And with all vertices, false. And this is not a traveling salesman problem. Let's go with 100 and number of ants 5. Okay, I've got an error over here. All right, so I actually bumped in an error, and with the help of the professor, we solved that error and came up with some new examples. So let's continue. First of all, I changed this part. It was graph before, but now it uses vertices. It doesn't matter, but vertices is more correct. And also, this line here, I changed it to the length of solution, not the number of vertices. This one is correct for the traveling salesman problem, but with a general view, it's not correct. And we also added some, changed some of the termination criteria here, and I think we added this to the code. And now let's go through the examples again. Okay, so the first example is a traveling salesman. Starting point, stopping point, and the ends visit all the nodes. After that, we have another example. So in this example, we want the ends to visit all vertices with the starting and stopping vertices. So starting and stopping vertices here are given. One time visit is false. Visit all vertices true. So as you can see, each time that we run the algorithm, we get a different path from 5 to 2 here. And for example, here we visited 2 twice, but the algorithm did not end here because with this condition, visit all vertices. So the algorithm needs to visit all vertices. Up until here, the algorithm did not visit all the vertices, so it needs to continue on to visit all the remaining vertices and finish it off here. That's also the case here. So it reached the destination point very soon without visiting all the remaining nodes. Therefore, it did not end there. And we have another one. This one is a generalization of the triangle inequality, but with one-time visit. So, starting vertex is 0, stopping vertex is 7, and visit all vertices false. One-time visit true. So each time that you run the code, you get the same answer, 0 to 7. As mentioned before, it's a generalization of the triangle inequality. So it says that, well, at least you can find one of the ends starting from 0 and reaching 7 because it's the just one path and there are no other constraints and other than one-time visit. So the solution will be 0 and 7, starting and stopping. The other example is again generalization of the triangle inequality, but without one-time visit. So it's the same thing. 5, 2, 5, 2. And again, because it's a generalization, somehow generalization of the triangle inequality. Start 5 and stopping vertex 2. Let's move on to the next example. Finding the closest point from the stopping vertex. So here, the starting vertex is null, and the stopping vertex is 2. So, this is 2. Oh, sorry, we have it here. So this is 2. And the closest to this one, I believe, might be this. Or maybe this. Yeah, this one. So let's see. Yes, 1, 2. So the starting point is 1, and the stopping point is 2. You can tweak this code, change this code, modify this code, and come up with new, I don't know, coordinates, maybe geographical coordinates of some places, and run the code and get results. And that concludes the fifth tutorial for EC457A. Goodbye.